let's see what you guys know from last year or 2 years ago. Okay, you guys are pretty familiar with what a Lewis structure is, so I'm not going to say that again. You're also pretty familiar with the octet rule, correct? What is essentially the octet rule in your own words? Why do they want 8?
Substable.
Okay, what does that mean?
Low energy.
Okay, all right. What the octet rule is essentially saying that when bonding, atoms tend to want to have 8 valence electrons, and the reason why they tend to want to have 8 valence electrons is because it makes them stable or have the lowest energy when they have 8 valence electrons, or an octet. Okay? So, let's start with some easy ones. Do it. I'm going to assume, or I'm hoping, that you guys can do all of these without my help, just as review from regular chemistry. And then I'll put them all on the board real quick, and we'll see if my assumption was correct, or if I have to spend a little bit of time reviewing, or if I can go right into the more difficult stuff and the exceptions. I would strongly encourage you to use pencil on these. These ones aren't overly difficult up to this point, but we will get through some ones that don't do what you would normally think they would do from what I taught you in chemistry, but since you have that foundation, it's a quick, easy fix once you learn how they need to be done. Any of these, we get wrong. Be honest, it's okay. I do not want to move on and if we can't do these ones. Good? How about that one? Gucci? You shook your head? Gooby? Let's see if we did this one right. You think you did this one right? Yeah, we did?
I know it is.
You know we did right? What? You gonna do the brackets, otherwise it look good? Okay. Just remember that when we have charges, we do the brackets with whatever the charge is. Okay, it tells us it's an ion versus not. Otherwise, good? Nice. nope, let's not do that yet. What? Did they hold up? No. All right, let's just talk about a few exceptions. Let's talk about BF. I don't know if you have any. Do you have any spots for this or no? There are some octet exceptions, things that don't need to have an octet. I'm going to kind of give you what goes on, why we don't have to maintain an octet, and certain things like that. First off, why do things bond? To become stable. Now, remember, the octet rule is really a suggestion. Here's why. So what the octet rule says is that things are most stable if they have 8. Does that mean that if they don't have 8, they aren't stable at all? No, it's just they're more stable with 8. Some things don't have the ability to get 8. For example, if I were to do B boron and bond it with fluorine, could you get boron to have 8 in this situation? Is there any way to get boron for boron to have 8? No. Okay, does that mean this is not more stable than boron and the fluorines by themselves? Well, we don't know that, but if it bonds like that, I mean, there's probably an assumption that we could easily make that would say this is more stable than if it were not bonded. Does this mean it's extremely stable? No. In fact, this is not extremely stable, it just happens to be a little bit more stable than the alternative. Does that make sense? So this is still really reactive, so much reactive that if an NH4 molecule were to come near it, okay, this is more stable than its unbonded form, but it's still very, very reactive because it isn't in the most stable state it could possibly be. So say NH4 comes along, boron BF3 looks at it and goes, ooh, I could bond here to become stable. So what ends up happening is these 2 electrons here are both shared with boron to form this guy. I think I was supposed to have hydrogens here, but it still does the purpose. Now do you see how boron has an octet? Nitrogen still has an octet, right? Okay, so what I'm trying to say here is the octet rule is one that says it's typically most stable with 8, but it's not always the case. Just because it doesn't have 8 doesn't mean they don't bond, just means they're not the most stable they could possibly be. So, this doesn't have 8, it still can be in this form, but it's still fairly reactive because it would be more stable if it could be in this state. Make sense? Okay? One of the octet exceptions. Let's talk about the second octet exception. There are quite a few. Well, let's look at this guy. What? Why is it doing this? Sulfur has how many around it? 12. How can this happen? Let's do the outer energy level orbital notation to kind of look at this. Okay? Based on this setup, this would agree if I were to do sulfur, dot notation, Q1 bonded electrons, would that agree? Okay? Now, a goofy thing can happen when you add the D sublevel into the equation here. Okay? What ends up happening in this particular case is if we were to take an experimental device and check out these bonds, what we would find is that these bonds are very, very close to identical in bond energy. Okay? Well, this puzzled chemists, and they had to come up with some sort of model to be able to explain why this sulfur can form 6 bonds. Here's what they came up with. It's introductory into chapter 9, which is that difficult chapter. It's called hybridization. What that model suggests is that when these compounds form and they bond, they actually create completely new hybrid orbitals. And that their initial orbitals that they had in their atom state aren't the same as the orbitals that they have when they bond. They hybridize, they form hybrid orbitals. So what they say is this electron goes here, this electron goes here, and then they form hybrid orbitals where all 6 of these form equal energy hybrid orbitals called sp3d2 hybrid orbitals. An orbital from S, 3 orbitals from P, and 2 orbitals from D. So there are 6 orbitals, and those orbitals are called sp3d2 hybrid orbitals. All of those orbitals have the same energy, versus in this situation, we would say that this, and this all have different energies, correct? With me? So when you were doing the electron configuration, see we fill the 3s first and then the 3p. It's hot here. Did we fill the 3s first, then the 3p, then the 3d? That was suggesting that they had different energies, correct? Okay. Well, the not the valence bond theory. What's it called? The orbital theory. It's something orbital theory. Suggests that these bonds are all very similar, so they should all have very similar orbitals. So they came up with this theory that said they actually, when they bond, they don't just overlap the orbitals that they originally had, they form completely new hybrid orbitals. So, here is some things that we have to talk about with regards to the octet rule. So how would I know, Mr. Kramer, if this is going to form SF4 or SF6? Or SF2? How do I know? Well, when can we disobey the octet rule and when can't we? Here's your answer. Whew! It's not as bad as you think. Okay, these are just some comments, they say, about the octet rule that we need to know. Okay, first and foremost, second row, second period, second energy level, guys, will always obey the octet rule. No matter what. They are not capable of disobeying the octet rule. Okay, except for boron, because it just can't obey the octet rule. Does that make sense? But these guys, always going to obey the octet rule. And here's the question. Why is that? Because the second energy level doesn't have what? What doesn't the second energy level have? Any idea? That would allow it to disobey the octet rule. D orbitals. Remember that little, what do we call that? A coffin or something like that? An example that said the first energy level only has what? S. The second has S and P. Third has SPD. Okay, so that should go to show you that anything in the third energy level or above have the ability to break the what? octet rule?
The 7th has S.
I don't know if you'll ever do any guys with the 7. Because typically when we're talking about Lewis structures, we're talking about nonmetals, which are those are radioactive guys that aren't even going to be very long-lived anyways. Okay? So, things you got to remember. Carbon, nitrogen, oxygen, fluorine will always obey the octet rule because all they have is an S and a P sublevel. They cannot form hybrid orbitals with the D because there's no D there. Okay, then it talks about here. Boron and beryllium will have fewer than 8, like the boron example I showed you. However, they are going to be very reactive because they don't have a full octet. Okay? Does that mean they're not more stable than if it wasn't bonded? No. If they're bonding because it's more stable to bond that way. Okay? Alright, third energy level, or third row and higher. Often satisfy the octet. Okay? But they can exceed the octet rule because they have what? D orbitals. Okay? Which would allow them to create hybrid orbitals and have more than 4 bonds around it. Okay? So, the question is, well, Mr. Kramer, how am I going to know how to do any of this stuff? How do I know if I have to obey the octet rule or not if I'm in the third energy level or above? Okay, so when writing Lewis structures for a molecule, satisfy the octet rule first. Okay? That's important. If you can satisfy the octet rule and it's good, great. If you get to it and you get the octet rule and you still notice that there are some electrons that remained unbonded, or some pairs that aren't bonded, or some things that aren't stable, okay, then place the element. Then it says take those unbonded electrons and place them on the elements with the D orbitals. So what that means is, if you're going to have guys that disobey the octet, they need to be on guys that can actually disobey the octet. That make sense? Everyone? Okay. Questions so far? Some of these are easier than others. You want to try to do all of them, and then we'll come together and I can show you how some of these goofy ones work, or what do you want to do? How do you want to do this? Start with it, and then, not you guys, well, unless you're using pen.
Just do like the first.
Well, the first one is real easy, or probably the easiest of all. The hardest ones are probably the ones with the charge. Now, okay, now, how don't you guys do this one? I think this one you won't find any difficulty with. So at least do the first one. They're going to do whatever they have to do to become stable. So keeping electrons on one particular element rigidly is not the best way to be successful when doing Lewis structures. They're going to do whatever they need to do to become stable. Now, what you do not want to do is you want to start bonding the guys not on the central atom with each other. What I mean by that is I do not want to see a chlorine-chlorine bond. That isn't going to happen. That might help you answer this question a little bit easier. Should have brought this flannel today. figure it out. I know you're like, we were told never to do that last year.
I thought there was like a couple.
There might have been a couple. Okay, so what's going to end up happening here is, yes, it will break up that lone pair. That is no longer off limits, just telling you that. The thing that does stay the same here is that every single bond is still going to be 2 electrons. Okay, just no longer has to be one from each. Does that make sense? Doesn't have to necessarily be one from each. You can unpair a pair that you normally wouldn't do. Okay? Now, I know there was a rule that said you're looking for your most unpaired electrons to figure out the central atom. Well, in this case, they both have one unpaired electron, so which is going to be the central atom? The most logical explanation in this case would be the Cl. It would not make sense to have one fluorine in the middle and then a chlorine and 2 fluorines around it. Okay, so let's look at it. So obviously I can only put 1 fluorine next to that unbonded pair, and then I'm going to have to probably do something interesting or different. Again, I am going to break up a lone pair. That's okay. Now notice, fluorine is one that can't disobey the octet, so that's another reason why you're not going to have fluorine in the middle. Chlorine can disobey the octet because it has what? D orbitals. So that is exactly why fluorine is not going to be in the middle. It cannot have more than an octet, but chlorine can have more than the octet. And if I were to look at this, 1, 2, 3, 4, or 10 electrons, looks like in this case, I would call this sp3d hybridized, which we'll talk about that at the beginning of chapter 9. Questions so far? Little goofy. Haven't got to the real hard ones yet. Next one, got our xenon. This one's a little goofy. No. Well, okay. We're going to talk at the end of this chapter because there actually is a variety of ways you could make this work, but there is one that's the best. We'll talk about the end of this chapter how we know which one's the best when we start talking about formal charge. You could form 3 triple bonds here. That is a possibility, but you'll find out at the end of this chapter why that's not the most likely. 1 and 1, voila. 1 and 1, voila. 1 and 1, voila. Then, since oxygen's so electronegative, it goes like this. Everybody see that? Well, I'm just going to take you because it makes me stable. And I'm just going to take you because it makes me stable. Now notice, if it can achieve an octet, it will. Look at xenon. Xenon has a what? Octet. And this is why it's probably most stable this way, but you'll see what they do to determine which is the most likely at the end of this chapter.
So if you can, that's why you don't do the double bond.
Yeah, because the double bond would not satisfy the octet. It would satisfy the octet for these guys, but it would not satisfy the octet here. So if you can find a way to satisfy the octet, do it. Now, on this one, there was no way for us to satisfy the octet without starting to do goofy things like putting chlorines into few spots. Okay? Alright. This one's not overly difficult. Now, this is probably not the best way for me to show this as far as structurally, because lone pairs repel differently than bonding pairs. And so if I were to do this correctly, I probably would do something like this. Something like that. Now, I'm not expecting you to do that. Okay, just talking about symmetry. We'll talk about the molecular geometry of each of these guys in this chapter as well. That's coming up, I think, next. All right. 5 disobeys the octet rule, but in a different way. Just like that. Now, it said in the comments about the octet rule that this is possible, but it's also very what? What was that? It's unstable. So it's very, very reactive. It's more stable than not bonding, but it's still very unstable. Okay? Let's end on the 2 more difficult guys. Well, at least I haven't looked at them, but anytime you've got your charge, they tend to be a little bit more challenging. I'll put the chlorines in the 4 locations here. We can always fix it or move it around after we figure out what is the best way to do this. All right? There's an easy one there. Let's just start forming single bonds. This one isn't overly difficult. Yeah, there is one more electron. Don't leave these guys unpaired. So I'm going to go like this, like that. Over here, and I'm going to take the extra electron, I'm going to put it on the central atom with the D sublevels. Like that.
Why is there an extra electron?
Good question. I'm not 100% sure.
How do you know that?
Well, I will tell you. It gave you.
Oh, because there's
charge.
4. Oh.
The negative charge means it gained an electron somewhere, not from an outside source. Because if these guys just bonded, it would be neutral, right? Now, I'm guessing the reason why there's another electron is it makes it more stable to have these guys paired than actually not. Okay? I'm not 100% sure why this guy has another electron. Okay? Last one. Three iodines. Now, I'm telling you guys, we'll have a little bit of struggle as you do some of these guys in your homework. That's okay. Let's form one here. Let's form one here. And then let's move this here and add another electron right there. Now notice where I'm disobeying the octet. It's always where? The central atom. Okay? That's always where I'm disobeying the octet. I need to charge on the outside here. Any questions? It's a feel. The thing you gotta remember is just remember some of those ideas about when you can disobey the octet, when you can't, And where you're going to typically disobey the octet is going to be on the central atom. Okay, and if you start forming some double bonds, and you could probably still get it to work, it's not that those are wrong, it's just you haven't learned enough information to know why the alternative is more stable. Okay, so you know, it's very possible that you might form double bonds on your homework, and it might not be the one that the book has, but it doesn't mean you're wrong. You just don't have the information to know why it's wrong. Okay? All right.